Hello, in this video we're going to look at recursive formulas. So in example 1 we had the sequence defined by the formula a sub k equals 3 times k. This is an example of an explicit formula. Most of the formulas for functions that you have encountered thus far are explicit formulas. However, there is another way to define a sequence using a recursive formula. Consider the terms from the example sequence 3, 6, 9, 12, 15, 18, 21, and so forth. If you were given this sequence in this form and asked to describe it, then you might start by saying that the first term is 3 and the terms increase by 3 each time. You add 3 to the previous term to get the next term. This description is a recursive formula for the sequence. In a recursive formula, we specify the first term, or sometimes the first few terms, and then we give a recursion relation that tells how to go from previous terms to later terms, usually just from one term to the next. In this example, we can write out the recursive formula for the sequence as follows. A sub 1 equals 3. That identifies the first term. And then we say a sub k is a sub k minus 1 plus 3 for k is greater than 1. So if k is 2, for example, to get a sub 2, we do a sub 2 minus 1. Well, 2 minus 1 is 1. A sub 1 is 3. Add 3, that gets 6, which is a sub 2. To get a sub 3, we take a sub 2 and add 3. To get the next one, we add 3 and 3 and 3 and 3 and so forth. So the second line is called the recursion relation. On one hand, this recursive formula is not as good as the explicit formula because with an explicit formula, we can easily compute the output for any particular input. For example, if we want to find a sub 200, we would take 3 times 200 equals 600. Just like that, we're in business. We've found that term without finding any other terms along the way. We can find a sub 200 with the recursive formula. We would start with 3, add 3 to get 6, that's a sub 2. Add 3 to that to get a sub 3, that's 9. Add 3 to that to get 12, which is a sub 4, and so forth, and so forth, and so forth, figuring out terms all the way from 2 to 199 before we could finally add 3 one last time to get the 200th term. So we could do it, but whew, that's a lot of work. An explicit formula is much better. So because of that, an explicit formula is generally preferred. On the other hand, the recursive formula does explain a structure in the sequence that might not be apparent from a cursory look at the explicit formula. So let's do an exercise. Write out the first 10 terms given by the following recursive formulas. A sub 1 equals 3, a sub k equals a sub k minus 1 plus 2 for k is greater than 1. That's the first one. For the second one, a sub 1 equals 3, and a sub k equals 2 times a sub k minus 1 for k is bigger than 1. And for part C, let's do this sequence. A sub 1 equals 1, and a sub 2 equals 2, and a sub k is a sub k minus 1 times a sub k minus 2 for k is greater than 2. Work these out yourselves and come back when you're done. Press pause now. Okay. Well, here's the first one. We start with 3. 3 plus 2 then is 5. 5 plus 2 is 7. Add 2 more, we get 9. Then 11, 13, 15, 17, 19, 21, and so forth. So you can see the nice pattern there. Start with 3 and just add 2 each time. Similarly, the second one starts with 3. We do the same each time, but this time it's not adding 2, it's multiplying by 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 gives us the 48. 48 times 2 is 96. Then multiply again by 2 to get 192, then 384, 768, and 1536. The last one we have to specify 2 terms. A sub 1 is 1 and a sub 2 is 2. And then we multiply the first 2, 1 times 2 to get 2. Then we multiply the next 2, 2 times 2 to get 4. Then 2 times 4 is 8. Multiply the 4 and the 8, the previous 2 terms, to get the 32. Multiply 8 times 32 to get 256. 32 times 256 is 8,192. Multiply those two terms to get this one, and then multiply these two terms to get the last one. The last couple there get really big, so it gets pretty big pretty fast. All right, now let's reverse it. That time I gave you the formulas, recursive formulas, and had you come up with the first terms and write the sequence out. This time it's pattern recognition. Fill out the next three terms and recursive formulas for the following sequences. And then also see if you can write out explicit formulas for the A and B lines. Work this out yourself and come back when you're done. Press pause now. Okay, let's see if you got these. So what we do on this first one is we're adding 4 each time to get the next term. 5 plus 4 is 9. 9 plus 4 is 13. Of course, we could find that by subtracting. 9 minus 5 is 4. 13 minus 9 is 4. 17 minus 13 is 4, and so forth. And I think every single time that pattern stays consistent. So there's a common difference of 4 between successive terms. So to get the next three terms, add 4 each time. 33 plus 4 is 37. Add 4 more is 41. Add 4 more, that's 45, and so forth. To write the formula for this, recursive formula, we would have a sub 1 is 5, and then a sub k is a sub k minus 1 plus 4. And that works for k is bigger than 1. You just have to be able to find the previous term and then add 4. Now, hopefully you've already seen this kind of function before. This is a linear function or arithmetic function, arithmetic sequence, we call it when we make it into a sequence. We know that the common difference is the change in y divided by delta x of 1 gives us a slope of that common difference, that change in y or change in a here, which is 4. So that's the slope. So we know the point goes through the point 1, 5 with the slope 4. A sub k is 4 times k minus 1 plus 5. The k minus 1 tells us how many times we add 4 to the 5. So when k is 1, we're not adding anything to the 5. When k is 2, we're adding 1 4 to the 5. When k is 3, we're adding 2 4s to the 5. See, we add 5 plus 4 gets us to 9, plus another 4 is 13. So we're adding 5 plus 4 plus 4 to get from 5 to 13. Or if you distribute this and combine like terms, this is 4k plus 1. This is an example of what we call an arithmetic sequence. It's just a linear function with a natural number domain. The next one is we multiply each term by 4 to get the next term. So again, we start with 5. A sub 1 is 5. But then a sub k is 4 times a sub k minus 1 for k is bigger than 1. So let's check that out. 5 times 4 is 20, times 4 is 80, times 4 is 320, times 4 is 1280, times 4 is 5,210. That's not right. I should have said it's actually pretty easy to do this. You just put in the 5. If we can say, it's pretty easy to do a recursive one here on the calculator. Say we say times 4, it'll take the answer times 4. So it should have been 20, 80, 320, 1,280, and 5120. Yeah, that was transposed there. I thought so. Okay. And let's see. To get the next terms, well, I can just continue on with my calculator. Let's see if I got them right here. Just keep hitting enter. It'll keep multiplying the answer by 4. Yes, that's correct. And then that one, that's correct. And that's correct. So these are correct. The next few terms. That's the correct thing. This is another type of function that you should have seen before. This is an exponential function. But when we have the domain as a natural number, we call it, instead of an exponential sequence, we call it a geometric sequence. The base is 4 is how much we're multiplying each time by the 5. So we start with the 5. We multiply by 4 k minus 1 times. Or if you'd like it just to be 4 to the k, it's 5 fourths times 4 to the k. Now the next one is a little interesting. You have to, the pattern here is add 1 plus 1 to get 2. 1 plus 2 is 3. Add 2 and 3 to get 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is, what is that? 55. Then we do 55 plus 34 is 89. And then 55 plus 89, that's wrong. That's a 4. That's not right. What's 55 plus 89? Let's see. 144, I think. Yeah, 144. And so here we have to specify we have to have two terms before to get going. So we need to specify the first two terms, A1 and A2 are both 1. And then we have this recursion relation, A sub k is A sub k minus 1 plus A sub k minus 2, and that works for k's greater than 2 for the third, fourth, fifth, and so forth. This is also a famous sequence. It's called the Fibonacci sequence. It's named after Leonardo Fibonacci da Pisa. Leonardo da Pisa, or also known as Fibonacci. So these three types of sequences are pretty famous and actually have a lot of physical applications. And we're going to talk specifically about arithmetic sequences and geometric sequences in the following two videos.